Welcome to the community of
engineers, the change agents in the society. Let's review the method of statics. In this, we will consider a structure designed to support a 30 kN load. Now, this 30 kN load is further supported by beam AB, which is of rectangular cross section of 30 by 50 mm in length, and a circular rod of BC that is of 20 mm diameter. And these are supported at pin B, A, and C. And here we have to calculate the external forces as a result of this 30 kN of load in the members and internal stresses produced in the member because of these external forces. To do that, we have to draw a free body diagram, and in free body diagram we see that at point A and point C there are reactions, and we have shown the components of these reactions and assuming that the direction of these components are unknown. So in fact we are getting responses at point A and C. To calculate these reactions or the responses, we are going to use the equilibrium conditions. First we take a moment about C. So we get that Ax into 0.6 meter minus 30 kilonewton 0.8 meter. So we get the value of Ax component, that is 40 kilonewton. So this is equation 1. Now summation of forces along x-axis 0. Now we have Ax plus Cx is equal to 0. We know the value of this Ax, so straightway we get the value of Cx, that is of minus 40 kilonewton. Now minus sign indicates the compression. Let's say this is equation 2. Now summation of forces along y-axis 0. Now that is going to be Ay plus Cy minus 30 kilonewton is equal to 0. So we are end up with this Ay plus Cy is equal to 30 kilonewton This is equation 3. Now, so far we found two unknowns out of total four unknowns. So we have to further disassemble the structure so taking a free body diagram of beam AB and again applying equilibrium conditions, in that summation of moment about B, so we are having minus AY 0.8 meter 0, so AY is going to be 0. This is equation 4. Now substituting equation 4 in equation 3, and equation 3 is AY plus CY is equal to 30 kilonewton. So 0 plus CY is equal to 30 kilonewton. So CY we are having 30 kilonewton. Now representing forces, these forces with regards to the vector form or the vectors, so we may write this AX is equal to 40 kilonewton, CX 40 kilonewton but in opposite direction, and CY is 30 kilonewton. What? Further note that the reaction at point A causing compression in the beam AB, that is, this is beam AB, and this force that is AB is causing compression. Now further, to calculate the reaction at C, we are having already the components of the reaction at C, that is Cx and Cy, and proportional to the horizontal and vertical components, we can calculate the reaction of C by 30 square plus 40 square simple trigonometric function, and we are having 50 kilonewton of force at C as a reaction. Now forces of the two members are going to be like this. Let's say this is beam AB, this is load, and here we are having load of 30 kilonewton. Here we are having compressive force that is of 40 kilonewton, and here we are having tensile force that is of 50 kilonewton, as shown as FBC, FAB. Now we have calculated the external forces which are caused in the member because of the load 30 kilonewton at point B. Now we are going to calculate the stresses. Now for stresses, let's first we consider the stresses at rod BC, and we know that there is a tensile force of 50 kilonewton. To calculate the stresses, we are having the expression that is sigma is equal to force upon the area, and we can calculate the area because we are having the diameter of 20 millimeter. So by using this expression, pi d square upon 4 or pi r square, we can calculate the area, an area that is of 314 10 raised power minus 6 meter square. Now using these values in this expression, we are having the stress in BC rod, that would be 50 into 10 raised power 3 Newton upon 314 10 raised power minus 6 meter square. So we are having sigma BC of value 159 megapascal. Now here the positive sign indicates the tension in the member or application of tensile stress. Further, suppose that this rod is replaced by material aluminum, which is having allowable stress of 100 megapascal. Now in this case, what would be the cross-sectional area or the diameter? What would be the diameter of the rod? To calculate that, we are going to use same expression, sigma allowable is equal to force upon the area. To calculate area, we can write this expression as force upon sigma allowable. So using values, first we will calculate the area, and then from this area we can calculate the diameter of this rod. So we know the value of this force, that is of 50 into 10 raised power 3 Newton upon the allowable stress, that is 100 into 10 raised power 6 Pascal. So the area is of 500 into 10 raised power minus 6 meter square. So we know that this area is equal to pi r square, or we may write this r is equal to a upon pi under root. So using this value, 500 into 10 raised power minus 6 meter square upon pi. So r is going to be 12.62 into 10 raised power minus 3 meters, and since d is 2r, so we are having the diameter of 25.2 millimeter. So we can see that if you know the allowable stress, then we can calculate the diameter of the rod or the cross-sectional area of the rod by this method. Now we are going to calculate the stresses in beam AB, and we would be using same expression sigma AB, force upon area. The force is of minus 40 kilonewton, and for area the beam is of rectangular cross section of 30 millimeter by 50 millimeter. So we can easily calculate the area by multiplying both 30 millimeter into 50 millimeter, and the cross sectional area is going to be 1500 into 10 raised power minus 6 meter square. So sigma AB is going to be using these values minus 40 to 10 raised power 3 Newton upon 1500 into 10 raised power minus 6 meter is going to be minus 26.7 megapascal. Now here negative sign indicates the compression or the compressive stresses in the beam. Now we are going to calculate the stresses in the pin, and these stresses are going to be in the form of transverse or shear stresses, and shear stresses are applying as a result of two non-collinear opposite forces at a phase in between. Now at this phase there is going to be the shear stress, and we can calculate this shear stress as tau is equal to force upon the area. Now area in this case is parallel to the applied load. Now at pin C we can calculate the shear stresses force upon area. Now here we see that the force is of 50 kilonewton, and area we can calculate by using this expression pi r square, that is of pi 25 by 2 square. So area is going to be 491 into 10 raised power minus 6 meter square. So tau c is going to be 50 10 raised power 3 Newton upon 491 into 10 raised power minus 6 meter square. So tau c is going to be 102 megapascal that is applicable are applied on this section or face DD dash. Now further we will calculate the stresses, the shear stresses at pin A. Now if we see the pin A, there is a this kind of scenario. The same force is applied force. This is of 40 kilonewton or whatsoever is its value that is going to apply on two parallel faces. Now this is the case of double shear. As we see here at E dash, the half of the force that is applying, and at face D dash, another half of the force that is applying. Now we can calculate the shear by using same expression tau at A, force upon the area. Here the force is of 20 into 10 raised power 3 Newton as half of the force that is being applied, and the area that is of same 491 into 10 raised power minus 6 meter square, because the pin diameter that is of 25 millimeter, and we have calculated in previous example, previous at pin C. So the value of tau, the shear stress at A, is going to be 40.7 megapascal. Now this is the case of double shear. The previous was the single shear. Now this we call as a case of single shear, and the next is of double shear. Now we are going to calculate the stresses at pin B. Here if we see the pin B, there are simultaneously three forces are acting. So there are in fact four faces which are subjected to the shear stresses. Now downward force of 30 kilonewton that is further divided into two. This is 15 kilonewton and this is again 15 kilonewton, and this is of 50 kilonewton, and two forces are acting on these sections of 20 kilonewton each. Now there are in fact four faces which are experiencing shear stresses. This E, G, H, J. On E and J there are same stresses, shear stresses. So considering face E and J. So same expression, tau at E is going to be force upon area. The force is of 15 kilonewton on area. We have already calculated, that is 491 into 10 raised power minus 6 meters square, because we have already calculated the pin diameter, that is of 25 millimeter. So tau E and tau J is going to be 30 megapascal. Similarly, on face G and H, using same expression, tau G force upon area. Now here the force is 25 into 10 raised power 3 Newton upon same area, 491 into 10 raised power minus 6 meters square. So tau G is equal to tau H, going to be 50.9 megapascal. Now next we are going to discuss the bearing stresses. Now bearing stresses are caused by the bearing forces. Bearing forces means one member pushes the other member. Let's say we have a member and this is held on a surface like this. Now there is a force which is acting downward like this. Now because of this, on this section there is going to be the direction outward. This is going to be bearing stress. Or if you have observed the columns in your homes, now this column is on the ground, let's say. Now here you must have observed the bearing stresses. Now here in this case, if we see the bracket at pin A, now this is going to be the situation where the beam is pushing this pin and pin is further pushing this bracket, and where the force is applying, if I draw like this half circle, Now let's say this is the bracket. Now as a result there are forces which are acting all along on this surface. Now here we can see that the distribution of force of rather forces are not uniform, not for magnitude and not for direction. Circular distribution of forces. Normally in structures these stresses, bearing stresses, are not going to cause the catastrophic failure, but but as a designer we should be able to understand and we should be able to calculate these bearing stresses. Usually the normal stresses and the shear stresses are causing the failure. Here in this case, let's say sigma bearing is going to be force upon area. Now force is of 40 kilonewton, and to calculate area we have to multiply this T with the diameter. So here the T is 30 millimeter, 25 millimeter. So we just use these values in this, that is 40 into 10 raised power 3 Newton upon 30 millimeter into 25 millimeter, and we are having the bearing stress that is of 32 megapascal. Now with this we end our discussion here.